Today we'll be discussing how to do hypothesis testing with z-tests. This corresponds to the example in your book in Chapter 8, beginning on page 177, if you'd like to look along. So the question that the chapter introduced is, how does knowing the calorie count of a coffee drink influence people's behavior? And what they were looking at is that in New York City, legislation was passed that requires all menus to contain calorie count information on it. And so they're interested in seeing if this actually has an impact on consumer behavior. And this is intended to be a way of reducing obesity rates, etc. So, what they looked at was data from before this legislation was passed and data after at Starbucks restaurants, and they found that before the legislation was passed, the average coffee order contained 247 calories with a standard deviation of 201 calories. And that after this change was made, they collected some data for a little bit of time and found that the average calorie count of an order was 232 calories per purchase. And this was based on a sample size of 1,000 individuals. So that brings us to hypothesis testing. And the first step in hypothesis testing is to determine what is the population or the populations that are involved, what is our comparison distribution, and what are the assumptions. Now, with the population, we're interested in finding out whether or not it's likely that our sample of 1,000 drinks were drawn from the original population of average calories per order before the legislation was passed. So when people didn't have information about that calorie count of their beverages. So those are the two populations of interest. Well, the first one being before, and the second one is based on our sample, is the population of calorie counts for drinks after menus publish this calorie count information. The second part is we're interested in finding out what is the comparison distribution. And in our case, because we have a sample and we're taking the mean of that sample and comparing it to a population, we're actually using a distribution of means. Now that whole exercise we did with the central limit theorem, talking about how a distribution of scores is different from a distribution of means, is important here because it has implications for what distribution we're using and therefore what the standard deviation of that distribution is. And so here's this example again from previous, we were talking about height, that the distribution of scores is much broader than that distribution of means. And so that means that we can't use the population standard deviation, but rather we need to use the standard error, which is the standard deviation of the distribution of means. So remember that when we do our calculations later on. So the third part of this first step is talking about assumptions. And because we're doing parametric tests and inferential statistics, we make a set of assumptions about the distribution of our scores that allow us to make generalizations or allow us to make inferences from our sample to that population. So the first assumption that we have is that the distribution of scores, or actually in this case, our distribution of means is approximately normal. And remember from the central limit theorem that even if the underlying distribution of scores is not normal, the distribution of means will approximate normality because we're sampling repeatedly and we're then using those samples to create the frequency distribution, those means of those samples to create the frequency distribution. We know that when we have at least 30 scores that mean is based on, that distribution is going to approximate a normal distribution. So as long as our score is 30 or greater, we should be okay there, the mean that we're based on. In this case, we're using an n of 1,000. That's certainly greater than 30, so we need this assumption. And the second assumption has to do with random selection. Did they actually randomly select the drink orders? Or did they just go and 3 or 4 different days. Well, we don't necessarily know that. It's unlikely they used random selection. It's often not possible to get access to all of the scores in a given population, and so we really can't use random selection. That means that we are limited in our generalizability, especially since what we're talking about is coffee drinks from Starbucks. And so we can really only say something about them, and then we also have to be careful if we're comparing scores from New York City to scores nationwide. That might be a little bit different as well. So be careful in your generalization if we can't necessarily meet random selection. And the last assumption is that the dependent variable is scale. And we do meet this assumption because our dependent variable is the calorie count of the beverages. And calorie counts can range from 0 to, oh gosh, I think the book said it was 1,200 calories in a single drink. So you know that the dependent variable is scale when you have somebody getting their unsweetened passion tea, or black coffee, which is calories of 0. Okay. So those are the 3 parts of step 1. And the second step now is that we need to state the null and the research hypotheses. And I've already stated them symbolically here at the bottom. And we are also talking about a two-tailed test. Okay, so we'll talk about a little bit about what that means in one of the future steps. But here we have our null hypothesis, the boring hypothesis, where the mu of population 1, which we can say is without information, and the mu of population 2 is with information. We're saying basically there's no difference between the two. And with the research hypothesis, then what we're saying is that these two population means are not the same. They're different. So with the null hypothesis, we could state it in words as say, the calorie content of drinks are the same when calorie information is on the menu compared to when it is not. Our research hypothesis then are that calorie content of drinks are different when calorie information is on the menu than when it's not. And so notice that we're not saying that they're lower, which is what the legislators were trying to say. That would be a one-tailed test, and we're going to talk about that later on. But for now, we're just going to focus on doing a two-tailed test. Two-tailed tests are the more common type of hypothesis test. It allows us to be open to the possibilities. Remember we talked about confirmation bias, where people like to look for evidence that support their research hypotheses, and they fail to look for evidence that disconfirms it. Well, it's good to be open to the possibility that you might be wrong. And so we leave the two-tailed test as being kind of more the standard. Okay, so that brings us to step 3, where we look at the characteristics of the comparison distribution. So from step 1, we know the comparison distribution is a distribution of means. And so when we list the characteristics, we want to list a measure of central tendency and a measure of variability. So here, the measure of central tendency is going to be the population mean. And in this case, we know that that population mean is the same as the mean of the scores, right? So the mean of the distribution of means is the same as the mean of the distribution of scores, and that is 247 calories. So now we need to find some measure of variability. And again, because we're using a distribution of means, we need to use the standard error, which is computed using the standard deviation of the distribution of scores in the population divided by the square root of the sample size. So we're estimating what that standard error is based on our sample size. So if we were going to substitute in our values, we'd see that we have 201 divided by the square root of 1,000, and we get 6.356. So those are our two characteristics of our comparison distribution. And so we might want to go ahead and start drawing this out, right? And we have your z-score scale right here, and we can put in our mean of the distribution of means of 247 and our standard error of 6.356. Okay, so now we need to go on to step 4, where we determine what are our critical values, our cutoffs for that two-tailed test. And again, just to remind you, here are our two hypotheses, our null hypothesis, that they're equivalent, and our alternative or research hypothesis, that they're different. So when we're determining what our cutoffs are, we have to set our type 1 error rate. It's also known as our p-value or alpha. Now, the type 1 error, remember, is when you get a false positive. So what's the likelihood that you reject the null hypothesis when you shouldn't? So what percent of the time would you be okay with doing that? Turns out most of the time researchers are okay with being wrong that way 5% of the time. So we commonly set our alpha value to be 0.05. Okay, so that's our proportion, or you could say 5%. So with a two-tailed test, what we do is we take the 5% type 1 error rate, alpha, and divide it evenly between the two tails of the distribution so that each tail has 2.5% of the scores. And we'll come back to this when we talk about one-tailed tests and how that might be different. But for now, what you need to know is we take that 5% and we put it in either end of the distribution because we're not hypothesizing that the mean is above or below. We're just saying that it's different. So here's what it would look like. So here we have our distribution, right? We just have that. We draw in and shade in what our critical values are. Now I got these values by going into the Z table in the back of the book and looking to see where can I find 2.5% in tail. So 0.025. And it turns out that that value is a positive 1.96 and a negative 1.96. So you can see why it's a two-tailed test because we have a tail here and a tail here, and each of those contain 2.5%. So that's what we mean when we say a two-tailed test. So now we finally get to the fun part. We get to calculate the test statistic. And so let's list our givens from our problem in the beginning. So first we have the population mean of 247 calories. We have the population standard deviation of 201. We have the mean of the sample, which is 232 calories, so the amount of calories per drink after they've posted the calorie counts on the menu. And then we have the number in our sample, which is 1,000. So what does the computation look like? Again, remember, we're using the standard error, and we did already compute this in step 3, but I just want to remind you that because our comparison distribution is a distribution of means, we need to use the standard error, and we have 6.356 as our standard error. So now we calculate the test statistic for Z, and you can see our formula is the mean of the sample minus the mean of the population divided by the standard error. And if we substitute in, we have 232 calories minus 247 divided by 6.356, which gives us a negative 2.36 as our test statistic. Okay. So what do we do with this? Well, that brings us to step 6. Here we get to make our decision. So what I did was I pulled out where we drew off our cutoffs from step 4, and I put in our negative 2.36 here. And you can see that that shaded in region, it falls within that shaded in region, so we can make a decision about this. That calculated Z falls beyond the cutoffs, and so therefore we reject the null hypothesis. So that means that there is a statistically significant difference between before and after the calorie counts are listed on the menu. So this is what we can say. If we were going to put it into context, we'd say significantly fewer calories are consumed when calories are posted on the menu at Starbucks, mean is 232 calories, than when the calorie counts are not posted. The mean is 247 calories with a Z-score of negative 2.36 and a probability of getting that score of less than 0.05. So this is the way we would report that Z statistic if we were going to write it up. So there you have it. That's how we go through the process of hypothesis testing. There's a couple more things that are important that I think you ought to know, and I'm going to create a second video that talks a little bit about some of those issues, but this is the basics.